Hello operating systems people, this is Gabriel Palmer, and today we are going to be talking about the properties that we can use to think about interfaces. There are a great many of these, and I do not go into all of them in this slide, but I go into many of them that you'll need to consider and think about when you talk about systems code. Okay, so we already talked about this idea of interfaces being immensely important. We talked about why they are effectively, in some sense, encoding the abstractions of your code. And if you remember, systems are about creating abstractions, which are easier to use for higher level things. Therefore, we really care about interfaces. Okay, but let's dive into that a little bit. They're really important because they define the resources available to make the system change, right? So resources might be memory pages, they might be CPUs, they might be files, directories, etc. But in some sense, the abstractions are the things that define those resources and how they are used, what operations can be performed on them. And it's also strange to think about it, but interfaces are in some sense a language, almost a programming language, that we use to formulate how we actually have a discussion with these resources. Right? If you think about a programming language, we think about all these different statements and whatnot. Well, the functions within your APIs are your statements for this language that is the interface. They also define protocols, and often these are not implicit, but protocols are relationships between the different functions that are typically used on certain resources. So for instance, opening a file, then reading and writing to it, and then closing. You can almost think of a state machine as describing the valid transitions to use on a specific resource, and this is a protocol. So the interfaces encode all of these things, and that makes them immensely important to kind of study and think about. So we all know how to write good interfaces, right? We've all been coding for a while. We know how to do this well, right? GG, easy. What's there to talk about? This is easy. Yeah, but not so much, right? Because it's really hard to put your finger on what differentiates a good from a bad interface, right? Maybe it's a type of thing where if you see it, you can kind of say it, but it's not always that way, and it's usually more subtle than that. And if we think about like the Windows API, POSIX API, Linux APIs, OS X, penny likes her apples, of course, we might kind of have some sort of just kind of knee-jerk reaction about kind of those notions, right? Windows is stodgy and has these kind of weird interactions with corporate whatever, right? POSIX and Unix are really old and you only have neckbeards using that, right? Linux is for geeks, and depending on who you talk to, it's kind of POSIX plus some sort of weird nuclear outgrowths that we call Linux. I like this graphic because it looks like the beak of a penguin. So forevermore, that's how I think about Linux for sure. And OS X is actually just kind of the mock microkernel mashed in a giant explosion with FreeBSD, which is a POSIX-based system to create an Apple, right? So we have all of these notions about all of these different interfaces, but it's really important to actually dive into the specifics about what makes a good interface versus a bad one, rather than having these knee-jerk reactions to broad swathes of interfaces, right? Anybody who says like any of these is good or bad is not really to be listened to, right? The truth is always much more complicated. So we just want to dive a little bit into this idea of how do we get some objective means to assess and understand interfaces. So we're going to go through a number of properties today, and the first one is composition. Compositionality has to do with the combination or the sequencing of different functions. So for instance, if we have a function f0, another one f1, and we have some specification for their behavior for some input. So f0 taking an input of a does x of a, right? Whatever that x is, you could specify it for different types of functions. And if y does a corresponding y of a. Then if we were to have a single function f of 0 called with a, b, and a as arguments, does it do that corresponding xa, xb, xa that we would expect? As we put these together one after the other, does the specification still hold? Furthermore, if you look at kind of the second example, well, we go from f0 to f1. Can we mix these functions within the API in a predictable way where they still accord to their specifications? And for a very good example of where this doesn't hold, let's look at the stirtoq. function. Strtoke, of course, tokenizes a string over subsequent calls to strtoke. So if you were to call strtoke with various strings over time, then it really starts to mess up because strtoke keeps a global variable that tracks where you are in a current string. So if you start passing various strings to it, it's probably not going to work as you expect it to. And you may think like it's kind of dumb in this example to call, strtoke in a way that kind of its man page says that you can't, right? But composition needs to also happen across different threads. So if we actually move the second strings manipulation into a second thread, well, now that feels like code that you should be able to write, right? But you cannot, because this ordering where you call it in, where the strtoke calls get called in this particular 1, 2, and 3 order across the two threads, that's going to break, right? So strtoke is not a composable API. Let's look at another example of lack of composition. This one's fairly famous because a lot of people who are into functional programming kind of made this argument, I think correctly so, that locks don't compose. And that statement takes a lot of processing, and instead of kind of stating tersely what it means, let's just go through a few examples. So let's imagine that we're maintaining some sort of accounts with some sort of balance within them. So we have these two functions, decrement the amount in an account and increment the amount in an account. And we want this to be able to run across multiple threads, so we have a lock with each of those accounts, right? And we do the corresponding minus of some amount or plus of some amount depending on the function. And we know that inc calling with 10 is going to work perfectly fine on its own. Dec on that same account with 10 is going to work perfectly fine. And if we want to transfer between two separate accounts, notice in the lower example we have the A and then B, that's actually not necessarily correct, because we could be preempted, or we could have a parallel operation executing on a different core in between that increment and decrement. Between the increment and decrement, a lock is not taken, so anything can happen, right? We've already taken 10 units away from account A, and we would expect that transfer semantics means that 10 units are now in B. But in fact, that's not the case here. We're in some sort of a weird limbo between dec and inc, whereby the whole system is essentially missing 10 units worth of currency, right? So that is not necessarily correct and is going to cause some very strange problems. If you try to sum up the amount of money in the system, it will vary in very strange ways where it goes away and comes back depending on interleavings. All of this is to say that this lock implementation works individually for dec and inc, but if we try to compose these two calls together into a more complex call, we cannot, because the behavior changes in subtle and hard to debug ways, right? So if we get the interleaving here, this is where things get very strange. Now, I do want to point out that I'm kind of simplifying here. This whole, and I'm sorry, this is an interlude. This implementation needs a little bit more love. It's not quite correct. Dec needs some sort of check in there, because if we try to decrement more money than is in the account, we probably want some sort of an error to trigger. So we might change our code to have better error checking, like here, where we check to see if the amount is greater than the balance. If it is, then we have some sort of an error. We have to remember to release the lock. That's very easy to forget to do on error paths, and then return some sort of an error, right? So we can't forget to do this stuff. I'm of course simplifying here, but you'll notice here that kind of that lock release inside of the condition is very, very easy to forget. The same applies for freeze. If we allocate some memory in this function and we get some error, then we need to free what we allocated, right? These are really, really hard to remember to do. So you always want to use your language features to make your life a little bit easier. So in C, for instance, you can use kind of local exception handling using, unfortunately, go-tos, but it is the way that you do it to do that. So now we've kind of made our error checking path share the same cleanup code as the main cleanup. There's a lot of information about this in the composite style guide I'm not going to go into here. So ignoring all of that, coming back to composition, if we wanted to implement some sort of a transfer function, we would now have to implement a separate function that takes both of the locks, and only when we're in both critical sections are we actually able to update the amounts without the previous issue that we saw before, right? The previous preemption that caused some money to disappear for some interleavings. So that's fine, but you see, now we don't have a composable API. Ink and Deck do not compose with respect to each other. So now we had to add another operation that is not just implemented using Deck and Ink because we cannot compose them. It needs to actually dive into the implementation of that module to make it work. So when you do not have composing functions, you often need to understand something about the actual implementation to make it work. And that's a very bad position to be in, right? You should not need to understand what's happening in the implementation when you want to compose two functions together. However, even this transfer function itself is wrong because it opens itself up to subtle errors. So we have this from and to, and what happens if we try to transfer between the two threads? Notice the A's and B's are reversed on the thread. Here we can get deadlock, and if you don't understand why, then watch the operating system lecture on deadlock. So even when we tried to manually compose these things together in our own operation, we got it wrong. So this is really hard to do right. Locks, this is all to say that locks are really difficult. Not only are they not compositional, but they're very difficult to get right. So what might we do? We might make a global lock for all of the accounts and kind of take that lock. But now Amdahl's law is telling us that, you know, we're now taking a lock that everyone needs to take. Therefore, we have these critical sections that is impacting everybody's progress. So this is not necessarily scalable. We'll get into why later in the class. So you might be even more clever and say, well, why don't we use that first implementation of transfer that takes the two locks, but make sure that we always take them in the same order, independent of what order they're passed in as arguments. So we might take the numerically lowest addressed account and always take that one first, and then take the numerically highest addressed account and take that. So you can see we're actually just taking them in the order of their literal pointer address, right? This seems like a massive hack, and in some sense it very much is, but this is actually the technique that underlies optimistic concurrency in most databases. So this is actually a very widely used technique. Okay, so going back to what composition is all about trying to create APIs in which complex behavior can be created from small operations by the client, right? We don't want to have the client understand the inner workings of everything to be able to compose functions together. We want them to do it naturally. And Unix pipes are made for composition, for instance, because the implementation within any operation within a shell pipeline doesn't really matter. We just need to know what it's spitting out as its output, and we can take that in as the next input. So you can pose together a lot of small programs to get more complex behavior out of Unix pipelines. We also want predictable behavior that's context insensitive. Context insensitive means, you know, it doesn't really matter as much which of the other functions have been called before or after it, right? Now, of course, if two functions by their semantics modify the same data, then they still composed if they're called one after the other because that's what they are supposed to do, right? So composition is usually with respect to their intended behavior. Additionally, if you have composition, then you should just be able to document each of the functions independently. If they do not compose, like the lock example that we talked about, then you need to disclose some internal information about the locks being taken so that the client can understand that if they try to use one function after the other, that this race could exist, right? So this is a big problem because it's effectively needing to expose the client to some of the implementation details, which breaks modularity because you're actually supposed to be able to have multiple different implementations for the same API. So needing to subsume some of the implementation details into the API means that reusability and replaceability is significantly weakened. So composition is usually one of those high-level things that we absolutely shoot for. Okay, what else? We also tend to focus on trying to implement APIs with that abide by the separation of concerns or are orthogonal. For the purposes of our discussion here, these are the same thing. These are synonymous. So the separation of concerns and orthogonality, what do these have to do with? Different functions within your API should cause different non-overlapping changes to the state within that module, to the system, right? Now that's a very long-winded and complex way to essentially say there's only one way to do it. If you want to update the account, call this function, right? So you might say that our previous API with the ink and deck is not necessarily abiding by the separation of concerns, because maybe you should just have a single function called modify that takes in a positive or negative value to determine how that account balance is changed, right? So if there's only one way to do it, then you're essentially separating out the implementation into these different functions, and each of the functions is responsible for a different portion of the API. However, when we talk about separation of concern, we're often usually also talking about, and it's much more important when you're talking between different interfaces in the system. If you have two different interfaces that interact with the same system state, then you have to worry in each of those interfaces how that state is being modified by the other. So now, again, we're having to think about and understand specific implementations and how they compose together to understand what the behavior is. You can imagine from the client's perspective, this is a big ask, right? And not something, if we're talking about modularity, that we want them to have to be concerned with. This is going directly against information hiding or encapsulation, right? So some examples where the separation of concerns is not applied is that in, for instance, Linux, there are many different ways to do interprocess communication. Signals, pipes, System 5 shared memory, mapped files, shared files, named pipes, Unix domain sockets, TCP, UDP sockets, dbus, binder on Android, etc., right? The list goes on. This is a lot of ways to do one thing, right? And you might even think, and in many cases this is true, some of these are completely redundant with each other. But the implementation with Linux has to consider every single interaction between each of these different abstractions. And if the internal state is modified by different of these, you have to, as a client, know that and understand that. So let's go through two examples. WinFS was in the early 2000s an initiative by Microsoft where they were actually trying to completely replace their file system with a backing database with something like SQL. And this was for a lot of reasons and would have had a lot of power having to do with kind of searching through the entire file system and whatnot. Apple went in a completely different direction and just said, yeah, you know what, let's keep the file system as it is. Let's just make good indices above the file system. Let's compose an index on top of the file system that can do good search. Guess which approach won out, right? Now, Windows essentially does the same thing by maintaining those indices. Part of the difficulty of this is that, and I'm not saying that this is why WinFS failed, but part of the difficulty of this is that when you're implementing a file system on top of SQL, there's an impulse to still expose some SQL interfaces to the user in some way. Some portion of the system should still be able to use SQL. But the file system is going to need some structure about it. It's not going to be it's not going to express every part of SQL. So now if you have raw SQL access to what's essentially the file system, and you execute some SQL update that updates that backing database in a way that the file system doesn't understand, it doesn't accord to the schema of that file system, what do? So now your file system, is it going to need to have error codes for all the cases where the data schema was updated in a way by the SQL transparently that you could not do with the file system? Unclear, right? So now you have two different interfaces that are essentially modifying and maintaining the same state. There's not a separation of concerns where there's one API responsible for maintaining that state. So this becomes very difficult. We have a little microcosm of that on POSIX systems. So mmap is a call where you can memory map a file and access it using load and store instructions, right? So it gets placed into virtual memory. Read and write, additionally, read and write from a file. But of course they use system calls to do so, right? So how do read and write that are reading and writing to a file interact with mmap, where you are loading and storing directly to that file? The client needs to understand that some uses of mmap and read and write might overlap. So if some portion of the system is doing reads and writes, let's say in some library that you don't even know about, to some file, you need to understand that that is modifying the mmap file that, for instance, your database is actually operating on. So in this case, we again have two APIs that are modifying the same backing state, and the client must be aware of all of those potential side effects, right? Okay, so that's the separation of concerns that, again, is a principle that we try to follow. There is certainly a strong argument that in the mmap versus read-write case that there is a justified reason that we do not follow the separation of concerns here, and that's that mmap is very powerful because it does allow us very fast access to the file at memory speed instead of system call speed, but read and write are still immensely useful because they are the polymorphic virtual file system API that we use to access the rest of the files, right, using normal APIs. But even that kind of breaks a little bit because you can't mmap all files. So this might be justified for performance and convenience reasons, but it does put more cognitive load on the user, on the documentation, and on the implementation. So you tend to not want to do these things, and when you need to do them, you better have good justifications. Okay, next, separation of mechanism and policy. This is one of the fundamental ways that we think about designing the layers or the modules and thinking about how different modules interact with each other. The whole idea here is that the core elements of how a system should be used, which we tend to think of as the policy, how we're actually using resources on the system, should be completely separate from the core system resource management or the mechanisms of the system. So what we define as a resource, again, is kind of dependent on which APIs you're using. But we tend to think of the resources provided by some API as being a mechanism that we can build functionality on top of. And that functionality uses those resources in a specific way that we define as the policy. If you have a composable API, then the policy might just be composing multiple functions and resources together to provide some higher level functionality. This again might be seen as, for instance, the pipelines within the shell, composing more complicated functionality from simple things. So some examples, and I really want to emphasize how this is kind of a layered system. An API at some level might be a mechanism to some policy, but that policy might expose an API that is treated as a mechanism to one of the higher levels of the system. So we might think of the Unix system calls as some mechanism that is used by the shell. So for instance, fork, dupe, close, etc., pipe are all system calls that are used by the shell to implement some policy, which is being able to type at the shell, compose different programs into pipelines, etc., right? And then how those pipelines are used is usually defined by the user or by shell scripts. So now the shell itself is actually being used as the mechanism to implement the higher level policy, which is the user pipelines. So system calls are orchestrated into a shell, and the shell is orchestrated into user pipelines. So you can see how the mechanism at one point is used to create a policy that then might be used as mechanism for the next higher level of abstraction. Some additional examples here. We might think of the mechanism of X Windows on Linux. I don't think modern X Windows, but older X Windows exposed a protocol that wasn't really opinionated about the Chrome on all of our windows. You know, what does the exit out of this window thing look like? What does the bar at the top of your window look like that you can drag around, right? That's Chrome. It didn't really have an opinion about that. Layout, yeah, it doesn't really have an opinion about that. You define that in the layout manager. So we have these policies, the Chrome, the layout, that use this raw mechanism of X windows that really is just composed with rasterizing things onto the screen and composing overlapping windows to decide which one to show, right? Or compositing them, sorry, not composing them. You might also think kind of on a more hardware level of atomic instructions being the mechanism that is used by the spin lock implementation to orchestrate locks, right? Spin locks use the mechanism of atomic instructions by adding policy to behave like something that provides critical sections, right? Interrupts, comparably, are a hardware abstraction that we use to provide preemptive scheduling as a policy. So you can see there are many, many mechanisms at all different levels, and they all just have to do with some sort of an interface that we interact with. They provide some raw resources and mechanisms. We use those in certain ways and provide services to higher level things. Our policies become mechanisms to them, right? So all three of these general goals very much fit together. The notion of composability, where we want to combine mechanisms into powerful policies, therefore it fits with this mechanism and policy separation. Orthogonality has to do with making APIs and functions cleaner so that we can combine them together in a predictable way. This enables us to compose those policies by using the mechanisms of that raw API in a powerful and easy to understand way. And the mechanism and policy separation enables us mechanisms to think about how to intentionally design the layers of the system. It makes us ask, what are the mechanisms that we're using? What is the policy that we're providing? And then what is the API that we should expose the outcome of that policy to the higher level portions of the system as our own mechanisms? So all three of these things are inextricably linked in a very powerful way, right? This is what I consider the trifecta of easy to use, easy to understand API. And again, you're never going to find an API that implements all of these perfectly. We always need to make trade-offs for performance, for conciseness, for simplicity, etc., etc. But these tend to be your go-to for what you're trying to focus on and provide by implementing an API. Okay. I'm going to talk about state management as kind of the next collection of different things that we consider for APIs. Now, these are not necessarily goals. These are more so properties, right? These are ways that we just kind of think, does an API manage state in this way? Okay, then I can assume this, right? That's kind of what we're looking for here. Okay, so liveness is really important. Every single API, must consider liveness. And this is mostly important for libraries, but also exists for most other APIs. When you're implementing a library that provides functional interfaces to some sort of a client, you always need to ask who owns the pointers being passed into that API. So one option is that the caller or the client, the thing that's passing the pointer in, actually owns them. If you own a pointer that you're passing in, then that caller can access the pointer after the function call. Because they own it, they can assume that it still is alive after the function returns. The callee has not deallocated it or made it invalid in some way. The caller is usually responsible for freeing the object in this case. If the caller owns it, then the caller must free it, right? Okay, so two examples. Example one, a service that stores objects in some sort of a data structure that can be retrieved later, right? So just imagine you have a data structure that stores objects, and you know, that's what you're left with. Now let's go through a case where the caller owns those objects that are going to be stored in the database if we implement that in this API. Okay, so the client will pass an object by reference into the library that has a data structure. The service itself, that library, will store the reference to the object in a data structure. Now the client owns the reference, but it's also stored within that service's data structure, right? But now, if the client owns that object and it knows it owns it, then it can also freely object. And if it can freely object, then that object's memory is no longer valid. So what happens to the object when within the data structure we dereference it and start accessing it, right? This is real bad. Faults can happen in this case, right? So if you need to store a reference to some sort of a pointer, then it doesn't usually make sense for the caller to be the one that owns it. Let's go through another example, just a simple service that returns the number of words in a string. So we pass in a string as an argument and it returns the number of words, right? So the client passes a string by reference, the service processes on the string, and then returns the number of words, but because the caller, the client, owns the reference to that string, it can then still access that string and it can free it. After that point, the service should not access that string, right? So this all makes sense. The service no longer is referencing that string because it doesn't own it. So therefore, all of this works. On the other hand, if we think that in an API, when we pass a reference to a pointer, the callee or the service owns that pointer from that point onwards, then everything changes, right? The callee, the service in the library, is now responsible for freeing the object. And the callee now defines the lifetime of that object. If it's stored in a data structure, then we know that that service is going to maintain that object as alive as long as it's within that data structure, right? Okay, so again, back to example 1, storing it in data structure. So the client passes the object by reference. Now the service owns that reference to that object, and the client cannot now dereference it because the client does not own it. It does not have access to it, right? No, it still has a pointer to it in C, but just because you have a pointer to something doesn't mean that you should actually dereference it, right? So the client can now make perhaps another call in the API, which might give it ownership of that object back. So for instance, if we're pushing into a stack and then popping, push, the owner becomes the service, the stack itself, right? But pop might return ownership to the client. So we know that we can't free it unless we own it on either side, right? Now there are APIs, for instance, in the kernel, so across the system call API, where the client determines how long some resource is accessed. So we can open a file, access it a whole bunch, and we can access it until we close that file descriptor, essentially, right? But the kernel still essentially owns it, right? It's only because it is exposing an API that allows the client to have a hand in its ownership. But in some sense, the kernel actually owns the references to the real file, right? Okay, let's go through the second example. We're trying to find a number of words in a string. The client passes a string by reference, fine. The service processes on the string, and then it frees the string. The service owns the string as it's being passed in, so it's no longer going to access it after this single call to count the number of words, so it must free the string, right? Because the service owns the string, the client cannot access it after this call returns, right? So this is really awkward, right? I just wanted to know the number of words in a string, and for some reason this function is deallocating the string, right? This is immensely awkward. So this points out that it's very important to specify who owns a string or who owns any pointer that you're passing into an API, especially if it's with a library. And I want to go through a few kind of conventional examples of how to think about this in C. We're going to be looking at a lot of C, of course, so you want to understand this. Rust, the programming language Rust, essentially encodes these types of liveness constraints into the language type system themselves. Okay, So let's imagine we have a few different functions, res init. So we have some sort of resource. It could be file init, it could be, data structure init, whatever. But we have some sort of a resource, and we have an init function on it, we have an alloc function on it, and we might have comparable deinitialize and free functions, right? Res deinitialize, res free. And you might ask, like, res init, res alloc, these feel pretty redundant, right? Both of them, you're kind of initializing some sort of data structure. So what's the difference? For resource init, the implementation of resource init does not own the resource that's being passed in. Instead, the client owns that resource being passed in. The implementation of the function's job is just to initialize that resource, but not to allocate, not to maintain a reference, none of that stuff, right? So the caller, the client of this API, is the one that owns that resource. On the other hand, for resource alloc, we do not actually take as an argument the resource itself. We allocate it using malloc. And after we malloc it, we usually call res init. I'm sorry, this is a typo here. It says init, it should say res init. So we allocate the memory, and then we call res init because, hey, res init knows how to initialize the fields within that structure, right? But then at that point, we currently own the implementation of all of that memory because we malloced it, but then we return it and pass ownership to the client. So it's very common in C to have this kind of separation between these two APIs that have different livenesses because we're either passing a resource in or not, simply because you want the init, because if the client wants to stack allocate a resource or globally allocate a resource, then you don't want to call malloc. So they want to call res init directly, whereas if you want it stored on the heap, then you can call res alloc, right? Okay, so that's what the two of them do. Deinitialize, effectively, it doesn't free the memory, it just deinitializes it. And then res free will actually call deinitialize and then free the memory itself. So this is a very common pair of types of functionalities that you see in C, because C gives you the ability to do stack and global allocation of different objects. Okay. Let's continue with the notion of state management. Liveness is one thing that you need to consider, but thread safety and reentrancy are others that are very important to understand and normally need to be published as part of the API. Notice that this is actually in some sense kind of breaking encapsulation, but it is something that you just almost always need to know in an API, especially for a library. So thread safety is simply the idea of whether you can have multiple cores or multiple threads, I should say, calling a function at effectively the same time because of concurrency or parallelism, right? So two threads calling the same function on two separate cores, two threads calling the same set of functions in an API on the same resource on separate cores. Is that allowed, yes or no? That's basically whether the function itself is thread safe. So can I call this function in separate threads without locks? If you can, then you know that there are probably locks inside of the implementation, but you as a client don't need to worry about that. You might need to read the specification for deadlock concerns, as we saw with the transfer function, right? So that might need to be encoded in documentation somewhere, right? However, if you do not have a thread-safe API, yeah, that's a big bummer. You either need to wrap the calls to that function in a lock yourself, or you need to ensure that effectively one thread calls it at a time in some other way, right? But this is really hard because what if a library calls that function and your client application calls that function? How do they both know the same lock to take to protect the data structure, right? So generally, this is one of those big questions, whether the API is thread safe or not. Most modern APIs are thread safe. Reentrancy is related, but based on different mechanisms, so therefore not that similar. And the idea is essentially, is a function safe to use in a signal or interrupt? Can a function be executing while that same function is executing in a lower stack frame, is essentially what it boils down to. So can we use it both in a thread and in an interrupting signal? So let's look at what this looks like. We have a thread that's executing along on its stack. Notice, remember that threads extend themselves downwards. So I will graphically show that as downwards. So we're executing the thread in blue, and let's say that thread calls malloc, right? Then we get a signal handler. A signal handler effectively saves all of the registers for that thread onto the stack and then executes a signal handler routine. Signals are common in Unix, right? And if that signal handler now calls malloc, is it possible that some sort of a bug could happen, right? This is a problem. This is effectively saying that the malloc call is not compositional with itself with respect to signals and interrupts, right? So in this case, almost all modern mallocs will blow up. Modern mallocs are not implemented in a way that they should be reentrant. And the reason we'll actually point out that reentrancy is often to the detriment of thread safety and vice versa. Malloc, you want to be thread safe. You don't want to have to call your own locks for malloc because doing so would cause massive serialization in the critical section of malloc. Malloc implementations themselves might use locks, but they'll probably use locks in a way that's relatively fine-grained for their own data structures, therefore achieving more parallelism, right? However, because malloc uses threads itself, if malloc, while it's executing in the thread in the blue as you see here on the stack, takes a lock, and then it's interrupted by a signal handler that tries to take the same lock, you have a problem, right? You're in a critical section and the same exact thread tries to take that same critical section. There's no way to resolve this in a sane way, so the system should actually blow up at that point. Because malloc is not reentrant, but it is thread safe, you can actually never use it in a signal handler. So there are implications here. Malloc, again, if it's not thread safe, then it makes it really hard to make it parallel and scalable on multiple cores. So it wants to be thread safe. But if it's a function is thread safe and it takes locks, then it often is not reentrant, right? So you have this really difficult interplay. So you really only see this in signal handlers that you really try to simplify and get rid of. Most signal handlers, all that they really do is write to a pipe that your normal loop in some thread can actually retrieve for this reason, because you can't even call malloc. You can't really do anything in a signal handler. But you also see it in interrupts at the lowest levels of your operating system. But because it's at the lowest levels of the operating systems, you know, we can create abstractions that hide that API relatively well. Okay, let's go on with state management. State management can also be used to describe stateless APIs. Stateless APIs, that's maybe a bad term. It should really be pure or functional APIs. The whole idea here is that if the output of a function only and solely depends on the input, then you have a pretty powerful API. It's very, very easy to test because it's just a correlation between inputs and outputs, and it's essentially the core of most functional programming languages. But I would like to say that these are not very relevant for operating systems or for a lot of stateful systems, simply because system services usually aren't stateless. They have some sort of internal global data that needs to be modified or will change the output for some sort of a function. Functions are not just solely a function of their input. They're a function of their input and the corresponding state of the system. So if we had some system service that was actually stateless, it was just dependent on the inputs to the function, there's no reason not to just implement that in a library, right? It doesn't need to be in a separate module with its own state. So we don't see this very much, so I'm going to go on. State management, again, let's push on. Idempotency is another property that we use to think about some APIs. Idempotency is a property whereby we can say if it's idempotent, then we can typically cache it, and we can typically replay operations in a sane way. So this is the goal here. We ask, is something idempotent, so that we can understand whether we can use caching and whether we can use replay. I'll get into those. So idempotency effectively means that we can repeat some sort of operation with the same input and we'll get the same output. So if, for instance, we have some sort of a key value store, all that it does is basically be a Python dictionary mapping keys to values. We can put a key with a corresponding value, and if that returns the value that we put into the key value store, and we call put twice, then we know that the value that we passed in and v1 and v2 should all be the same. That we called put twice doesn't really matter. It just kind of overwrites what was there already, but what was there already is exactly the same value that we put before. Therefore, the operation is idempotent. Get, more importantly, is idempotent, right? Because if we call get with the same key twice, we should get the same value out both times. So what this means is that if we can get something twice and we get the same value back, that once we get the value back once, maybe we can cache it so that we don't need to ask for the value that second time. Instead, we can just get it locally. So this is used very frequently on remote systems, right? And on the basis for a lot of superscalars or cloud systems. So that's where this is mostly important, but idempotency appears within a lot of file system APIs as well, which allow us to cache file contents. Replayability I will get into later. It's a little conceptual, so we need to talk about it later when we talk about event APIs with respect to level and edge triggering. Okay, and then I believe the last big one that I want to talk about is commutativity. I'm not going to go into this in too gory of details because we will talk about it a lot in the third component of the class. But the big question here is, do two functions commute in a mathematical sense, right? And that is to say that the behavior of a function is semantically identical regardless of the order of those multiple function executions. So here we see on the left and the right two different orders of the open call to two separate functions. And intuitively you might think, like, you know, opening a file on the left and opening a file on the right, like A and B, like it really, these should not really be any different whatsoever, right? We're asking for two separate files, so they should open just the same on the left as on the right. But technically, the open call does not commute. Neither does any call that explicitly creates a new file descriptor in accordance with POSIX specification. So POSIX, for open, dupe, all of these system calls that will create new file descriptors, are specified that they should return the numerically lowest free file descriptor. If you look into the XV6 simple Unix, you'll see that this is actually how it's implemented. And if you look at how the shell is implemented, it assumes that this guarantee is made when it's actually creating pipelines. So this is what POSIX specifies, and therefore we know that file descriptor 1 and file descriptor 2 on the left and the right are semantically different. From a behavioral perspective, we know that file descriptor 1 on the left will be numerically lower, guaranteed, than file descriptor 2. On the right, the opposite, right? File descriptor 2 will be numerically lower. So these do not compose because the outputs actually are specified in a way where the semantics of those two calls will be different. The open of A will be different on the left as opposed to the right. So they do not commute because of this. We'll see later that has huge implementation implications for parallel systems. So what a lot of systems do to actually get rid of this constraint is they just modify POSIX. So they add extensions ++ to POSIX for open, dupe, and whatnot, where they essentially say you can return any free file descriptor. Now the specification essentially says that, you know, FD1 and FD2 can be anything. So they can be anything regardless of what order you return them in, right? Anything, again, I'm specifying here, anything means any of the free file descriptors that are not in use. So these actually do commute with that change. So why do we talk about commutativity at all? Commutative interfaces imply some sort of an implementation independence between two separate calls to different data structures. So if we think about the same function, open, being called twice with two separate files, if these are commutative, then we can implement or should be able to implement that in such a way that is parallel, which is to say that the data structures touched and modified by those two separate calls can be disjoint. If we do not have a commutative API, that typically means that the two operations needed to have some sort of a shared portion of a data structure that they were both modifying. So you can have a mental model for this saying, well, if it's commutative, then maybe we don't need to have the same lock being taken because we aren't accessing the same portions of the data structures for the two operations. However, if they do not commute, then that implies that they need to interact with each other somehow through the data structure, which means they need to take a shared lock, right? So if we have a commutative interface, we think that the scalable implementations can exist. Can is an important word here. You can, of course, not implement it scalably. Okay, and then the last thing that I want to go over is the notion of simplicity, or the principle of least astonishment. These do mean different things. I'm going to conflate them for simplicity here, regardless. So I'm going to just leverage kind of our intuitive notions here. I'm not going to strictly define this. You can find the book for a little bit more of a discussion of this. But, you know, the API should be as simple to understand, easy to use, and behave in a predictable manner. Right? These are all very subjective, so you can get into endless discussions about all of these things, but there are some proxies for these types of things. The number of arguments to functions might be seen as kind of contributing to a lack of simplicity in being able to understand and use functions if there are many arguments. If we expect the client to go through many different levels in a type, then that could be seen as relatively difficult to use. If you look at how over Unix domain sockets, we can pass file descriptors between separate processes, you'll understand what I mean. The amount that you need to navigate through the types is pretty complex, so that's not a simple API. If there are subtle differences in different functions, that could mean that they aren't very simple. It also probably means that they don't follow separation of concerns. But most importantly, when we talk about whether kind of a function behaves predictably, that usually means that it fits into the development philosophy for that API and for the surrounding development environment. So that's something that in and of itself is always going to be very touchy-feely, right? So you need to, I don't know, recognize that these are all subjective and not discuss them infinitely. Realize that they're all fallible and try to do the best thing given the information that you have and be willing to go back and change it. Okay, so in summary, I've talked about the interfaces in the system and a lot of their different properties. We talked about 3 principles by which you can use to think about whether APIs are effective or not. Whether they're composable, whether you follow the separation of concerns, and whether the modules follow the separation of mechanism and policy, right? So we can think about these 3 things as defining a set of stronger APIs than those are not as strong. But sometimes in following these strictly, you give up performance, so you need to poke holes in that, right? This is often some form of a leaky abstraction that I talk about in the book. And then we talked about a number of properties having to do usually with the state that's manipulated on different APIs that you have to understand to be able to use them appropriately, and you should document them where possible. So we want to understand the properties of these abstractions so that we can try to design them well. Throughout the class, you're going to be reading a ton of code, and I want you to keep all of these things in mind as we go through it all. Thank you very much. Have a good one.